Welcome back today on statistical machine learning. So today I'm going to talk about two exercises that we recently did, but I will only be focusing on one. So I'm just going to give a brief overview of the one that I will talk about the least. This one involved comparing 6 KNN models to classify the MNIST data, and it was really an interesting exercise. There are a lot of things to learn about the complexity, binary classification, and so now I'm going to go back to the first exercise, which was a DNA microarray gene initialization. So we have our data that has gene sample levels among 79 subjects, and we have 500 features for predicting if that subject has cancer or not. So this is simply a classification task. And so looking at the distribution, it is slightly imbalanced. There are slightly more number of subjects that have cancer than those that have not. And so one of the things that I did was did a Kruskal-Wallis test statistics to identify the 9 most powerful variable predictors. And this test, basically what it does, it tries to identify the variable that is likely to contribute to one of the classes, as in one of the variables that is likely to be used in the classification. And so these are plot of all the predictors with the Kruskal-Wallis test. It varies for the classes. There are a few that have very high test statistics and very low. And just looking at the box plot for the 9 most powerful predictor variables, you can see that they can clearly distinguish between the patterns between the response variable, that is 0 for the non-cancerous and 1 for the non-cancerous, and comparing it with a box plot for the weakest variables. There's a significant difference. The weakest variable are unable to differentiate between 0 and 1, that is cancerous and non-cancerous. And so doing a correlation plot for the top 9 predictors, most variables are most of them are correlated with one another, so it tells us about something that we will need to perform, or we might need to perform in other cases, so that we can only use the variables that will contribute to the classes that we are looking for. And so sorry about that. So I also did an eigenvalue decomposition, and the eigenvalue ratio of 17 suggests that the correlation matrix is highly ill-conditioned, and this just means strong multicollinearity, and if we want to use it, we might need to add regularization. And so I'm just going to the comparison of how the six machine learning models work. The first one was 1NN. As you can see from the ROC curve, it's perfect. It's basically overfitting the data. It's memorizing the data and now predicting the classes. You can see 7NN, 9NN, and the tree with different complexities, 0, 0.5, and 0.1. Basically, the tree with the highest complexity also has a similar performance to the 1NN. It's very close because since it's very complex, it's just memorizing the data. Moving on, this is the structure for the tree. As you can see, the tree with CP equals to 0 is very complex. It has the highest number of leaves than the two other trees. The two other trees are same because increasing or decreasing the complexity to 0.1 does not change anything. So it just means that a tree with CP 0.05 is the best tree, is the optimal tree. And just looking at the box plot for comparison, the 1NN has the smallest test error, but a few outliers. Basically, it is just memorizing the data, and using it in a classification task will be suicidal. Moving on to the ANOVA, the table represents significant differences in test errors according to the 6 learning machines. And looking at the p-value, we can clearly see that uh, these differences between altering the complexity is not just a random chance. Altering the complexity affects the accuracy and the test error of any learning models. And so those are some of the key takeaways that I can talk about. Uh, KNN models, increasing the KNN models reduces the complexity, and that means you will be just generalizing and getting poor test errors. So it is important to balance between selecting a complex model and a simple model.